So our next speaker is Aubrey Jackson. She's coming from Red Rocks Community College, and she has academic and research interests in environmental engineering and ecology.
Thank you so much, Alicia. So for my project, I assessed biogeochemical heterogeneity in a subalpine wetland. And I want to thank my mentors, Molly Huber and Hinckley, for all of their help and support, and also the RECCS program, the University of Colorado Boulder, INSTAAR, and of course, the LTER long-term ecological research station over up in Niwot. Next slide. A wetland is an ecosystem which depends on recurrent flooding or saturation of the landscape and soil. This is a wetland located in the subalpine of the Rocky Mountains in Colorado, and the water which runs through this wetland is assumed to enter the Boulder watershed. I'm focusing on heterogeneity of biogeochemical processes within this wetland, which basically means there are different processes happening all at the same time within this space. Spatial and temporal differences in oxidation and reduction reactions drive nutrient cycling within this ecosystem. Variation in the array of natural physical features within a wetland can influence its function and lead to differences in rates of nutrient cycling. This function allows wetlands to disproportionately affect their surrounding landscapes and have an influence on water quality. Therefore, an assessment of this variation can help us understand a wetland's function and influence. There are many different ways that you can measure biogeochemistry. Because of time constraints, I decided to look at the indicators of biogeochemistry. ORP is so oxidation reduction potential, or ORP, is essentially a measure of electron availability or stored energy. Dissolved oxygen tells us how much oxygen is in the water, and pH is a measure of proton availability. Next slide. I wanted to see if there was a pattern in biogeochemistry in this wetland across space. I categorized the variation in surface characteristics to assess how these characteristics influence biogeochemistry, and also to see if there's any recognizable patterns between them. I used variation in surface characteristics to assess how this variation influences nutrient cycling. So you can see here, these are the 3 ways that I categorized water level. The left picture shows saturated soil, and the middle is flooded water, so basically where there's standing water. And then the far right is a hummock, and a hummock is essentially a plant island that is lifted up out of the landscape. I took measurements of ORP, dissolved oxygen, and pH at 105 points in surface water across this wetland, and I grouped them into 21 nodes. I categorized them based off of dominant plant community and this water level that I just explained. Here is the results of ORP mapped across the wetland. You can see here in the legend that the color corresponds with the value of oxidation reduction potential in millivolts. The size stands for the standard deviation. So this was how far apart each measurement was, because there are 5 points grouped at each one of these mapped points. The water flows from northwest to southeast. There was no clear pattern along the flow line or at the input or output sites. For example, there's no cluster of pink at the top or yellow to the bottom. I found these differences occur at much smaller scales. And if you look at the legion, the range of measurements from -60 to 90 millivolts shows variability overall. Next slide. Oh, and right there is the flow line. I don't believe that animation was put in there. That is the flow line. Okay, next slide. Overall, there was no statistically difference in pH and ORP between the surface characteristics. And if you'll go ahead and click for me. However, the dissolved oxygen in flooded areas was statistically higher than the other characteristics. If you could click for me. This is interesting because of the lack of difference in ORP. A higher ORP is generally associated with a more oxygenating environment. However, my results did not indicate this in the flooded ORP. This makes me wonder if there is some other factor driving the nutrient cycling within this wetland besides oxygen availability. So what is next? Future work that I would like to see is the flow paths within this wetland on a smaller scale. So not necessarily just where the water flows in and out, but on a sub-meter scale, the different streams that exist within this wetland. What nutrients are important for driving biogeochemical cycling within this area, and at what rates is this nutrient cycling happening? Are there any questions?
Okay, excellent. We'll give a few seconds here for some questions to come in.
Got a question, Aubrey.
Yes.
Just making sure you can hear me. So you mentioned that there were other factors that could be driving the nutrient cycling. Do you have any theories about what those might be?
This ecosystem is so diverse that it's very hard to say. It's a little bit outside of the scope of what we looked at. However, one of the things that could definitely drive differences in nutrient cycling is the dominant nutrient present, which is why I suggested a kind of catalog of the nutrient concentrations within this wetland.
Great, we have another question. How do these nutrients affect the rest of the ecosystem in this area?
That is something that is also a little bit outside of our scope. Generally, the reason why wetlands are important is because their nutrient cycling can affect the surrounding landscape and the water quality. So the hypothesis is that water that is entering this wetland is leaving different. So I think it's a little more complicated than that.
Yes. Well, I think you have a lot of complicated systems in there. So great job. We're going to go ahead and transition on to our next speaker.